I'm going to tell you a story about nanomachines that read and write information in DNA, and how we're using those as a laboratory to probe the interplay of matter, energy, and information at the nanoscale. And to be provocative, I've also inserted consciousness in there. So I hope at the end of this to be even more provocative and have a little bit of time for Q&A where you guys can attack me. Okay, so I run a research incubator called NanoBioSim that really works at the convergence of fundamental physics, biomedicine, nanoscience, and information science and technology. And the one part is a research incubator institute that works on sort of some of these fundamental science questions, incubates new technologies. We've spun out a company, and we have one part that looks into ways of saving the world. Here you see a picture of rural Mississippi, where I grew up, spent a lot of my early childhood meditating in nature, wondering about the big questions of the universe. And I was struck by this idea that there's got to be an underlying wholeness or unity in nature, and the same laws of math and physics that we use to understand the far reaches of the universe must be applicable to understand life and living systems. However, the deeper I went in the study of both physics and the life sciences, first at Stanford, Harvard, MIT, and all these nice places, the more aware I became of how deep this divide really is. And I was encouraged to see that that Einstein, at the end of his life, came to a similar conclusion, that one can best appreciate how primitive physics still is by studying living systems. And just to elaborate on that a bit, most of our modern physics was developed in the context of inanimate matter. And Paul referenced Schrodinger's book, What is Life?, which was a great inspiration to me as well. And the mathematical machinery that we have was developed in the context of closed systems, primarily where the interaction with the environment is usually a perturbation. But living systems are fundamentally open systems. They exchange matter, energy, and information with their environment in a very strongly coupled way. And most of biology and medicine is practiced at the level of chemistry and molecular biology, with very little integration with some of the great advances that have happened in physics, whether they be the role of electromagnetic fields, mechanical forces, in how physiological processes occur. So it struck me that there's a whole new vista when we can break down these reductionistic silos and that have made tremendous progress in the last century, both in physics and in the life sciences, and bring them together. So now I'm going to share with you some other ideas. 100 years ago, Albert Einstein gave us a framework to understand matter and energy on some kind of equivalent footing. I believe that as we've gathered here today to try to come to terms with things like life, living systems, consciousness, we're going to need an equally, if not more radical transformation in fundamental physics, where we make matter, energy, and information, and even consciousness on some kind of equivalent footing. And we'll leave you with that and come back to that. So about 20 years ago, I fell in love with these things. These are tiny nanomachines that read and write information in DNA. These are little molecular Xerox machines that process the information, not only that's encoded, the biological information that's encoded in the bases of DNA, but process a ton of information that's embedded in its local environment to decide how to read and write the information into DNA. Now, the traditional thinking is that most of the information is just encoded in DNA, and these nanomachines are just playing out that blueprint. I hypothesize that there's got to be a lot of interplay between the information embedded in the DNA and the stuff that is encoded in the DNA. And that these nanomachines are really information processing machines or devices that are somewhat intelligent and that are making decisions based on how to read the DNA, when to stop, when to start, when to go back, and the fundamental fine structure dynamics that are influenced by stimuli from the environment. And we know, for example, just to take kind of a simple example, you could have two people with the same oncogene, which is a cancer-causing gene, and one may develop cancer and the other one may not. And we surmise that the only difference is the environment, because the DNA is the same. So I needed a way to experimentally probe these systems. Otherwise, it was all going to become philosophy. So I wanted to bring both the tools from modern physics, quantum optics, and other kinds of tools to start to probe these nanomachines at the single molecule level, and also make it sort of a laboratory in which we could bring tools and concepts from theoretical physics to more rigorously analyze this system as a way to probe this matter-energy information interplay. So what unfolds is a little bit of that story. So let's go into the next slide. So over the last several years, my lab has been looking at using these molecular Xerox machines, developing new kinds of tools, nano tools, to take a molecule of DNA, stretch it out in real time, and visualize the real-time dynamics of this nanomotor as it's replicating the DNA molecule. And we've won many awards and funding from these kinds of agencies. But some of the applications we've created out of this more fundamental science question is we've actually turned it on its head. So if these nanomachines can sense information about their environment, or they can process it, well, why can't we harness them as next generation nanosensing tools or technologies? So we've actually built some nanosensors that start to exploit this capability of this nanomachine processing information from its environment to pick up information that's relevant in various kinds of technologies. And the US military and other people are very interested in these kinds of things: genomic sensing, biological sensing, other kinds of ways of picking up information on very small scales about their local environment. And what we've done in converting this from a fundamental scientific insight into a technology is embed some of these fundamental, what I call nanobiophysics capabilities into technologies like microfluidics, MEMS, and nanofluidic devices to actually build devices. And we've spun out a company that's built one of our first generation devices, of a device called Gene Radar, which is a way of diagnosing disease in a mobile device. And recently won the X Prize. Well, thank you. And this is just the tip of the iceberg. When you take these very small sensors and embed them in next generation technologies, you can really build all kinds of smaller and smaller gadgets to start picking up information about people's own health. And it's called quantizing yourself, or various parameters. And those kinds of technologies are disrupting large multi-billion-dollar diagnostic companies. Each of these machines, these are old-fashioned machines based on a 20-year-old Nobel Prize-winning paradigm called PCR. Each one of these machines costs $150,000 and can take weeks and months sometimes to give you a diagnosis. And this kind of nanotechnology-based system can displace something like that. So I'm going to come back to basic science now. So one of our platform capabilities is the ability to precision control these nanomachines as they read and write DNA at the single molecule level. And this leads to a number of cool technological applications. Highly efficient energy transduction, the ability to read and write DNA with high precision, Gene Radar, which is a little more commercialized now, so I already mentioned that. But some things I want to focus on in this talk is that I think is relevant to this audience and the discussions we're having is, think of this as an information storage device. And these nanomachines are the read-write machines that are reading and writing information into the storage device. And also, could this be processing information quantum mechanically? And if so, could biology have already invented the first quantum computer? So I'm going to examine some of those questions. Not going to talk about that right now. So this is some of the things we can do in my lab. We can take a single molecule of DNA, stretch it out with lasers, light, tightly focused laser beams, and visualize in real time as a nanomotor, this nanomachine, actually assembles the double helix. So it sits right here. It picks up nucleotides from the environment. These are molecules like ATP. And we can record in real time, measure the position versus time of the motor as it's running along the DNA railroad track. And if we increase things in the environment, if we play with the environment, like play with the physical forces on the DNA, DNA is actually like an elastic rubber band. So we increase the mechanical force, we can actually slow down this motor as it's xeroxing this gene. So we're slowing down the process of gene replication. And if we pull hard enough, we can actually make the motor stall dead in its tracks, which is really stopping the gene from replicating. And if we go even crazier and pull even harder, we can turn the motor into a mode where it's doing error correction, where it's unzipping the bases that it's already incorporated and going backwards. And this is actually, I'll come back to the error correction piece. But this is just the tip of the iceberg of what other information is embedded in the environment that's talking to this nanomotor as it's xeroxing the DNA. And if you want to read more, you can read some of my papers where we talk about how by tuning the tension on the DNA, we can tune the speed at which the motor xeroxes DNA, and how certain macroscopic knobs in our lab at the environmental, in the environment can be used to control the movement of these motors at the nanoscale. And what and I don't have time to get into it, but I want to just mention, just to whet your appetite, that what's happening here when the motor's running backwards is a form of nanoscale error correction, which these motors naturally do as part of their replication of the genetic code. So when I was giving a talk someplace, one of the editors, Scientific American, got interested, it was the Indian editor, I guess, got interested in this concept. So I did an article here, which you might enjoy reading, and they really enjoyed they took the theme of tuning DNA strings to the next level. I could pause for questions now, but I thought you guys could think about that for a second. So one of the things that we can also do is probe this motion on very, very fine scales, and we see that it's not a continuous motion, it's actually discontinuous. I don't have time to get into that, but we've started to look at that as looking at different models, like thinking of the motor as a Brownian ratchet or a Maxwell's demon, just to get insights into how it's transducing chemical energy into mechanical work. Paul Davies, who's I have the honor of going right after, was really an inspiration to me in how to apply some of these tools and techniques and my own journey into these nanomachines in trying to understand whether they could be quantum mechanical in nature, and could they be an example of quantum mechanics playing a non-trivial role in life and living systems. So I have a chapter in this book of his. And so I'm going to just talk to you a little bit about that. So think about, I talked about precision control of these nanomachines. Now I'm going to start to get a little more speculative. Think about quantum controlling these machines. What does that mean? That means controlling their internal states as they're evolving. And why is that important? Just like in precision control, all those applications came out. Well, what if we could quantum control these nanomachines? Well, there's quite a lot of little speculative applications. One is, what is the role of quantum information processing and understanding the fundamental laws of life? Could these nanomotors be doing quantum computing or quantum information processing? Could this become a practical and scalable quantum computing architecture? Does it satisfy, for example, the Di Lorenzo, I can't pronounce it, criteria? Could quantum mechanics play a role in molecular evolution, the evolution of biological information? And I'll come back to all those things. So this is a little bit of a roadmap. I don't have time to get into all of this, but I'll just give you a little bit of a snapshot. So we talked about precision controlling nanomotors that read and write DNA. I'm going to give you a little hint of my paper in Paul's book about looking at the motor as a quantum computer or a quantum clock, applying Eugene Wigner's quantum clock inequalities to the motor. Look at the problem of decoherence in these systems. I don't have time to talk about this, but I designed what would be the equivalent of a double slit experiment in these systems to see if these nanomachines operate quantum mechanically and how we would harness them. So I don't have time to cover all this, so I'll just give you a snapshot. You can think of the motor as a quantum computer or a quantum clock. You define a state function of the motor as a superposition of these internal states of the motor. It's like an algorithmic state machine, cycling through these internal states to achieve external movement along the DNA. And as you're playing with different knobs in the environment, you have operators operating on these states, and those operators can be functions of different knobs in the environment. I don't have time to go into all this, so I'm just going to whiz right through because I'm getting a time signal here. So Eugene Wigner, and you can read more about this in Paul's book, in my chapter there. Eugene Wigner applied these, he derived these inequalities of fundamental constraints that quantum mechanics imposes on the measurements of space-time intervals. And they're popularly known as these Wigner inequalities. And we looked at applying them to a black hole. Actually, John Barrow did that, applied to a black hole, and found that the maximum running time, which is like the accuracy of, in the Wigner clock inequality, corresponds to a Hawking lifetime of a black hole. The lambda, the length scale in this inequality, the Schwarzschild radius of a black hole. And the precision, or the minimum time, which is another way of saying the uncertainty principle, is the fastest possible information processing frequency of a black hole. So I said, well, why can't we apply this to the nanomotor? So simply applying, and we discussed this in this paper, but applying the constants for the length scale and the mass of the nanomotor, you come up with order of magnitude estimates of the maximum running time of a nanomotor, and it corresponds roughly on the order of same magnitude. It's very heuristic on the error rate. So the motor can run about 100 seconds, this flavor, before it generates an error. And the precision, being the lifetime of an internal transition state, this is like the minimum unit of time the motor can register new information. So I don't have time to get into this, but one bottom line here is that the motor generates, roughly with this calculation, it's all in paper, 10 to 11th computational steps per every base that it's reading. So for every DNA base that it's reading. That means it has a remarkable information processing capacity. And my hypothesis is a lot of that is from its processing information inputs from the environment. I'm going to skip this decoherence piece because we don't have time, but it's all in the paper. The bottom line is the decoherence time of these motors, macromolecular systems, can be long compared to the critical base reading time, which opens the door for quantum mechanics to play a non-trivial role. So I'm going to skip all this and just tell you that can the environment play a role in directing molecular evolution, and is there context-dependent information that's encoded and processed? And perhaps this is a tool to start investigating some of those things. Okay, so I'm gonna, how much time do I have? 2 minutes, okay. So I'm trying to rush through various themes. So the discussion, Max, that you and Christoph and Julie were having, I wanted to just throw out this definition more to start being a little more provocative, of physical intelligence. Think of physical intelligence, and this is a simplistic definition applied to these nanomachines, where we define intelligence of the machine or organism or this information processing device as the ratio of information extracted by this machine divided by information contained in its environment. So, as we, I want to hear the audience reaction on this. I don't have time to get into all these thoughts, but I do want to say the following. I think that the prevailing paradigm, both at this conference and in modern science, seems to be that life, mind, consciousness are emergent phenomena that occur when matter attains a critical degree of complexity. I would like to invite you to consider an alternate worldview, one where information, consciousness, mind are something pervasive, more primal, even more fundamental than matter, energy, or even space-time. And things like matter, energy, and space-time are emergent phenomena that come out of that. And I'm going to share with you two inspirations of my own. Freeman Dyson, I think our consciousness is not a passive epiphenomena carried along by the chemical events in our brains, but is an active agent forcing the molecular complexes to make choices between one quantum state and another. In other words, mind is already inherent in every electron, and the processes of human consciousness differ only in degree, but not in kind, from the process of choice between quantum states, which we call chance, when they are made by electrons. Next, John Wheeler. It from bit symbolizes the idea that every item of the physical world has at bottom, at a very deep bottom in most instances, an immaterial source and explanation. In short, that all things physical are information theoretic in origin, and this is a participatory universe. I'm just going to leave you with that and happy to take any questions.